There is a number written on a whiteboard at CERN that should not be what it is. The number is 125.1. It represents the mass of the Higgs boson in gigaelectronvolts, measured to extraordinary precision by two independent detectors buried 300 feet underground on the border between France and Switzerland. 125.1. When that number was confirmed in 2012, champagne was opened, Nobel Prizes were awarded, and the discovery was celebrated as the crowning achievement of particle physics. The standard model was complete. The last missing piece had been found. The architecture of reality was understood. Almost no one mentioned what the number actually meant, because 125.1 is not a safe number. It is not a comfortable number. It is not the number that physicists hope to find. It sits in a narrow window, a razor-thin slice of possible values that places the entire universe in a state that physicists describe with a word they do not use lightly: metastable. Not stable, not unstable, metastable. Balanced on a knife edge between existence and annihilation, sitting in a valley that is not the lowest valley, perched on a ledge above a drop so deep that if the universe ever slips off it, every atom, every molecule, every star, every planet, every thought that has ever occurred inside every brain that has ever existed will be rewritten from the ground up at the speed of light, with no warning, no escape, and no possibility that anything recognizable will survive. The universe is slowly erasing itself, and we can measure it. The measurement is 125.1. If that sentence disturbs you the way it disturbs physicists, stay with us. Like and subscribe, because this is not speculation. This is not a thought experiment. This is a prediction that emerges directly from the confirmed physics of the Higgs field, the most precisely tested quantum field theory in history. The prediction has been checked. The mathematics has been verified. The number has been measured twice. And the answer, every single time, lands in the danger zone. Let us begin with the field that makes you possible and that might unmake everything. You are made of atoms. You learned this in school. Protons, neutrons, electrons, the building blocks of matter. But what makes those atoms possible? What gives the electron its mass? What gives the quarks inside the proton their mass? What determines the strength of the forces that hold everything together? The answer, discovered theoretically in 1964 and confirmed experimentally in 2012, is a quantum field that permeates every point in the universe. It has no gaps. It has no edges. It fills all of space the way water fills an ocean, and every particle that moves through it interacts with it in a specific way that gives that particle its particular mass. The field is called the Higgs field, and, unlike every other quantum field in the standard model, the Higgs field has a property that is both essential for your existence and potentially catastrophic for the existence of everything. Most quantum fields have their lowest energy state at zero. When nothing is happening, when the field is in its vacuum state, the field value is zero, empty, quiet. The Higgs field is different. Its lowest energy state is not at zero. Its lowest energy state, the state it naturally settles into, has a non-zero value everywhere in space. The field is always on. Even in the emptiest vacuum, in the deepest void between galaxies, in a region of space where no particle has passed for 1 billion years, the Higgs field is there, holding a specific non-zero value, approximately 246 gigaelectronvolts. That non-zero vacuum value is what gives particles their mass. An electron moving through the Higgs field interacts with it constantly, and that interaction manifests as the electron having mass. A top quark interacts more strongly and has more mass. A photon does not interact with the Higgs field at all and has zero mass. The masses of all fundamental particles, the numbers that determine the size of atoms, the strength of chemical bonds, the behavior of every material in the universe, are set by how strongly each particle couples to the Higgs field's vacuum value. If the vacuum value changed, everything would change with it. Not slowly, not gradually, instantly. The masses of particles would shift. The forces between them would restructure. Atoms as we know them would cease to exist. Chemistry would stop. Biology would stop. The physical laws that permit stars and planets and oceans and brains would be replaced by different laws that almost certainly do not permit any of those things. And here is the question that 125.1 answers in a way that no one wanted. Is the current vacuum value of the Higgs field truly the lowest energy state? Is the universe sitting at the bottom of the deepest possible valley in the energy landscape? Or is it sitting in a local minimum, a valley that looks like the bottom, but that has a deeper valley somewhere else, separated by a barrier that the universe could, given enough time, tunnel through? The mass of the Higgs boson determines the shape of the energy landscape. A heavy Higgs boson means a deep, stable valley. The universe is safe. A light Higgs boson means a shallow valley with a deeper one nearby. The universe is metastable, perched, temporary. 125.1 gigaelectronvolts is light. Lighter than stability requires. Light enough to place the universe squarely in the metastable zone. The universe is not sitting at the bottom, it is sitting on a shelf. And the shelf has an expiration date. To understand why 125.1 is dangerous, you need to understand something about quantum field theory that most popular accounts skip because it requires holding two ideas in your mind simultaneously. The first idea is the energy landscape. The second idea is quantum tunneling. Together, they describe a mechanism by which the universe can destroy itself. The energy landscape of the Higgs field is called the effective potential. It is a mathematical function that describes how much energy is stored in the Higgs field at every possible field value. Think of it as a landscape of hills and valleys. The field naturally rolls to the lowest point it can find, just as a ball rolls to the bottom of a bowl. The current state of the universe corresponds to the field sitting at a specific point in this landscape, the electroweak vacuum, at a field value of 246 gigaelectronvolts. If the effective potential has only one valley, one global minimum, then the electroweak vacuum is the true vacuum. The universe is stable. It will sit at this point forever. Nothing can dislodge it, because there is nowhere lower to go. But if the effective potential has a second valley, a deeper one at a much higher field value, then the electroweak vacuum is not the true vacuum. It is a false vacuum, a local minimum, a temporary resting place. The universe sits there because there is a barrier between it and the deeper valley, and rolling over that barrier requires more energy than the field currently has. The shape of the effective potential depends on the masses of the particles in the standard model. Specifically, it depends on the Higgs boson mass and the top quark mass. The top quark is the heaviest known fundamental particle, approximately 173 gigaelectronvolts. Its interactions with the Higgs field pull the effective potential downward at high field values. If the top quark is heavy enough and the Higgs boson is light enough, the effective potential develops a second minimum at a field value vastly larger than the current one, deeper than the current one, more energetically favorable. The measured values, Higgs mass 125.1 and top quark mass approximately 173, sit in the region of parameter space where the effective potential does develop a second, deeper minimum. The universe is in a false vacuum. Now for the second idea, quantum tunneling. In classical physics, a ball sitting in a valley cannot get out unless it has enough energy to roll over the hill. If the hill is too high and the ball does not have enough energy, it stays in the valley forever. In quantum mechanics, the ball can get out even without enough energy. This is quantum tunneling. It is not a metaphor. It is not an approximation. It is a confirmed, measured, experimentally verified phenomenon that occurs in every semiconductor, in every electronic device you own. Electrons tunnel through barriers. Protons tunnel through potential walls in nuclear fusion. Alpha particles tunnel out of atomic nuclei during radioactive decay. Tunneling is real. It happens. It happens constantly. It is one of the foundational phenomena of quantum physics. The probability of tunneling depends on the width and height of the barrier. A tall, wide barrier has a very low tunneling probability. A short, narrow barrier has a higher one. The tunneling probability is never zero. Given enough time, any quantum system will tunnel through any finite barrier. Any quantum system, including the Higgs field, including the vacuum of the universe. If the universe is in a false vacuum, then there is a non-zero probability per unit time, per unit volume, that a region of space will tunnel from the false vacuum to the true vacuum. The tunneling would not happen everywhere at once. It would begin at a single point, a single location in space where the Higgs field, through a quantum fluctuation, tunnels through the barrier to the deeper minimum. At that point, a bubble of true vacuum would form. Inside the bubble, the Higgs field has a different value. The laws of physics inside the bubble are different. The masses of particles are different. The forces are different. Chemistry is different. Everything is different. And the bubble expands, at the speed of light, in every direction simultaneously. The wall of the bubble, the boundary between the false vacuum outside and the true vacuum inside, propagates outward at the maximum speed the universe allows. Nothing can outrun it. No signal can precede it. No warning can arrive before it does. Because the warning itself, travelling at the speed of light, cannot move faster than the bubble wall, which also moves at the speed of light. If such a bubble nucleated anywhere in the observable universe, you would not see it coming. The last thing you would perceive would be whatever you were perceiving at the moment the bubble wall reached you. Then, the Higgs field at your location would shift to its new value. Every particle in your body would acquire a new mass. Every force holding your atoms together would change. Every chemical bond would break or reform according to the new physics. You would not experience pain. You would not experience anything. The transition would be faster than the time required for a single neural signal to cross a single synapse. You would simply cease to exist as a physical structure, and whatever replaced you would bear no resemblance to anything recognizable as matter, life, or thought. This is vacuum decay. This is what the physics predicts. And the probability, while extremely small per unit time, per unit volume, is not zero. Let us talk about the probability, because the probability is where the comfort lives and where the comfort dies. The rate of vacuum decay, the probability that a bubble of true vacuum nucleates somewhere in the observable universe per unit time, has been calculated multiple times by multiple research groups using the full machinery of quantum field theory. The calculation involves what is called a bounce solution, a specific field configuration that describes the tunneling event, originally formulated by Sidney Coleman and Frank DeLucia in a landmark 1980 paper that remains one of the most cited papers in theoretical physics. Coleman and DeLucia showed that in a theory with gravity, the tunneling rate is exponentially suppressed. The exponential factor depends on the difference in energy between the false vacuum and the true vacuum, the height and width of the barrier separating them, and the gravitational effects of the energy density involved. For the specific case of the standard model Higgs field, with the measured values of the Higgs and top quark masses, the tunneling rate is extraordinarily small. How small? The half-life of the false vacuum, the time over which there is a 50% probability of a decay event occurring somewhere in the observable universe, has been estimated at approximately 10 to the power of 100 years or more. Some calculations give 10 to the power of 200. Some give 10 to the power of 600. The exact number depends on the precise values of the Higgs mass, the top quark mass, and the strong coupling constant, all of which have measurement uncertainties that propagate into enormous uncertainty in the decay rate. 10 to the 100 years. For comparison, the universe is 13.8 billion years old. That is approximately 1.38 times 10 to the power of 10 years. The ratio of the vacuum decay half-life to the current age of the universe is approximately 10 to the 90. The universe would need to exist for a time period that is a 1 followed by 90 zeros times longer than it has already existed, before there is a coin flip chance of vacuum decay occurring. That sounds safe. That sounds very safe. And in a narrow, technical, actuarial sense, it is safe. You are not going to die from vacuum decay tomorrow. The probability of a decay event occurring in your lifetime, or in the lifetime of the Sun, or in the lifetime of every star in the observable universe, is so small that it might as well be zero for all practical purposes. But there are three things about this probability that should stop the comfort from settling in too deeply. The first is that the probability is not zero. It is exponentially small. It is unimaginably small. But it is not zero. And in a universe that may last forever, in a universe whose future extends infinitely into time, if the cosmological constant is truly constant, an event with non-zero probability will eventually occur. Vacuum decay is not a question of if. In an infinite future, it is a question of when. The universe is living on borrowed time. The loan is extraordinarily long, but it is not permanent. The second thing is that the calculation depends on physics we may not fully understand. The standard model calculation assumes that the standard model is the complete description of particle physics up to the energy scales relevant for vacuum decay. If there is new physics beyond the standard model, particles or forces or interactions that we have not yet discovered, the effective potential could be different. The barrier could be thinner or shorter. The decay rate could be faster. Or the barrier could be taller and the vacuum could be absolutely stable. We do not know. The uncertainty is not in the calculation. The calculation is precise. The uncertainty is in the theory. We are calculating the decay rate of a system whose complete description we may not possess. The third thing is the most unsettling. The probability is per unit volume, per unit time. It is not just a function of when, it is a function of where and how much space is available. The observable universe contains approximately 4 × 10⁻80 cubic meters of space. But the unobservable universe, the regions beyond our cosmic horizon that we will never see but that are governed by the same physics, could be vastly larger. In eternal inflation, the total volume of space is infinite. And in an infinite volume, even an exponentially suppressed rate per unit volume produces an expected number of events that is infinite. Somewhere, in some unimaginably distant region of an infinite universe, a bubble of true vacuum may have already nucleated. It may be expanding right now at the speed of light, consuming space and rewriting physics as it goes. It will never reach us because the space between us and the bubble is expanding faster than the bubble can cross it, thanks to dark energy. But its existence, if the universe is infinite, is not improbable. It is expected. It is a mathematical certainty in an infinite volume. The universe may already be erasing itself. Somewhere, right now. We would never know. There is a specific piece of the calculation that deserves its own treatment, because it sits at the center of everything, and because it reveals something about the nature of reality that most people never encounter. It is called the running of the coupling constants, and it is the mechanism by which the Higgs field's stability is determined. In quantum field theory, the strength of an interaction between particles is not fixed. It changes with the energy scale at which you measure it. The electromagnetic coupling, the measure of how strongly charged particles interact with photons, increases slightly at higher energies. The strong coupling, the measure of how strongly quarks interact with gluons, decreases at higher energies. These changes are called running. The coupling constants run. They change their value depending on how hard you look, how much energy you use to probe them. The Higgs self-coupling, the parameter that describes how strongly the Higgs field interacts with itself, also runs. And its running is what determines the shape of the effective potential at high field values. At low energies, the energies we probe in particle colliders, the Higgs self-coupling is positive. A positive self-coupling means the potential curves upward at high field values. The valley we sit in has walls. The universe is stable. But as you go to higher energies, the Higgs self-coupling decreases. It decreases because of quantum corrections from the top quark. The top quark, the heaviest fundamental particle, interacts very strongly with the Higgs field, and that interaction drives the self-coupling downward as the energy scale increases. At some extremely high energy, the self-coupling passes through zero and becomes negative. A negative self-coupling means the potential curves downward at high field values. The valley we sit in no longer has walls on one side. There is a deeper valley beyond. The universe is metastable. The energy at which this happens, the energy at which the Higgs self-coupling changes sign, is called the instability scale. For the measured values of the Higgs and top quark masses, the instability scale is approximately 10 to the power of 10 to the power of 12 gigaelectronvolts. That is far above the energies we can probe in any laboratory. It is far above the energies present anywhere in the current universe, except perhaps in the most extreme astrophysical environments. But it is a finite number. It is a calculable number, and it marks the point beyond which the Higgs field's potential turns downward and the universe's stability is no longer guaranteed. The running of the Higgs self-coupling is not a theoretical speculation. It is a calculation performed using the renormalization group equations of the Standard Model, equations that have been tested to extraordinary precision at collider energies. The prediction that the self-coupling turns negative at high energies is a robust result of the Standard Model. It depends on the measured values of the Higgs mass, the top quark mass, and the strong coupling constant. All three have been measured. All three point to the same conclusion. The self-coupling turns negative. The potential develops a second minimum. The vacuum is metastable. The precision of this conclusion depends on the precision of the measurements. The Higgs mass is known to about 0.2%. The top quark mass is known to about 0.5%. The strong coupling constant is known to about 1%. These are impressive precisions, but the stability calculation is exquisitely sensitive to these inputs. A shift of just 2 gigaelectronvolts in the top quark mass, well within the current measurement uncertainty, could push the universe from metastable into fully stable. A shift in the other direction could push it into fully unstable, meaning the barrier between the false vacuum and the true vacuum would vanish entirely, and the universe would be decaying right now. The universe's fate hangs on the third decimal place of measurements made in underground laboratories. The difference between eternal stability and eventual annihilation is smaller than the current error bars on the mass of the heaviest quark. This should make you uncomfortable. Not because vacuum decay is imminent, it is not, but because the question of whether the universe is fundamentally stable or fundamentally doomed is a question that depends on measurements we have not yet made with sufficient precision. We are living in a universe whose long-term prognosis is literally uncertain because our instruments are not yet precise enough to read the thermometer. Now consider what vacuum decay would actually look like. Not from the outside, because there is no outside. From the perspective of a hypothetical observer who somehow became aware of an approaching bubble of true vacuum and had the instruments to study it. This is, of course, impossible in practice. The bubble wall travels at the speed of light. You cannot see it coming because the light from its approach arrives at the same time as the wall itself. But in the theoretical limit, if you could observe it, what would you see? The bubble nucleates at a point, a single location in space where the Higgs field quantum tunnels through the barrier. At the moment of nucleation, the bubble is extraordinarily small, on the order of 10 to the minus 26 centimeters in radius, smaller than an atomic nucleus by many orders of magnitude. Inside the bubble, the Higgs field sits at the true vacuum value. Outside, it remains at the false vacuum value. The bubble wall begins expanding. The expansion is driven by the energy difference between the false vacuum and the true vacuum. The energy released as the field rolls from the false vacuum to the true vacuum is converted into kinetic energy of the wall. The wall accelerates. In a flat space-time without gravity, it quickly approaches the speed of light and continues expanding forever. In our universe, with gravity and dark energy, the situation is slightly more complex. The positive cosmological constant, the dark energy that drives the accelerating expansion of the universe, works against the bubble. If the bubble is too small, the outward pressure from the cosmological constant can overcome the energy release from the vacuum transition, and the bubble collapses before it can grow. There is a critical radius, a minimum size the bubble must reach before it becomes self-sustaining and expands forever. Below the critical radius, the bubble dies. Above it, the bubble lives and grows without limit. The critical radius depends on the energy difference between vacua and the cosmological constant. For the standard model parameters, the critical radius is extraordinarily small, and the probability of a bubble exceeding it is included in the tunneling rate calculation. The bubbles that matter, the ones that destroy universes, are the ones that nucleate above the critical radius and then expand forever. As the bubble expands, the wall carries enormous energy. The energy density at the wall is concentrated in a thin shell, a membrane of destructive potential expanding at light speed. Behind the wall, inside the bubble, the physics is different. Ahead of the wall, outside the bubble, the physics is normal. The boundary between them is sharp, essentially infinitely thin on macroscopic scales. When the wall reaches a region of normal matter, say a star, a planet, or a person, the Higgs field at that location transitions instantaneously from the false vacuum value to the true vacuum value. Every particle at that location acquires a new mass. The electron mass changes, the quark masses change, the W and Z boson masses change. The strengths of the electromagnetic and weak forces change. The consequences cascade at the speed of chemistry. Atoms that were stable become unstable. Atoms that were unstable might become stable. But different atoms with different properties obeying different rules. Molecules disintegrate, not violently in the way that a bomb destroys a building, more fundamentally than that. The rules that defined what a molecule is have been rewritten. The concept of the molecule you were made of no longer applies. It is not that your molecules are broken, it is that the category molecule, as you understood it, no longer exists in the new physics. A human being in the path of a vacuum decay bubble would not experience destruction. Destruction implies a process with a duration. The transition is faster than any physical process in the human body, faster than a nerve impulse, faster than a chemical reaction, faster than the time it takes a photon to cross an atomic nucleus. The human being would simply stop being a human being. The matter that composed them would be reorganized according to the new physical laws, instantaneously, on timescales shorter than any timescale relevant to biology or chemistry or even atomic physics. There is no pain in this scenario. There is no awareness of the transition. There is nothing. The bubble wall arrives and the person ceases to exist as a person in the same instant. No suffering, no horror, no experience of any kind. Just the boundary, moving at the speed of light, converting one set of physical laws into another. In a sense, it is the most merciful apocalypse imaginable. No warning means no dread. No duration means no suffering. No survivors means no grief. The universe ends not with a bang or a whimper, but with a phase transition, a change of state, the way water freezes or boils, except the water is space-time itself, and the change is irreversible and total. But the mercy is cold comfort to anyone who values existence over the absence of suffering. Let us return to the Higgs boson and the measurement that started all of this, because the story of how that measurement was made is itself a story about the relationship between knowledge and danger, and it deserves to be told carefully. The Higgs boson was the last undiscovered particle predicted by the Standard Model. Its existence had been proposed independently in 1964 by 6 physicists working in 3 groups: Peter Higgs in Edinburgh, François Englert and Robert Brout in Brussels, Gerald Guralnick, Carl Hagen and Tom Kibble in London. Each group described a mechanism by which a scalar field with a non-zero vacuum value could give mass to the gauge bosons of the weak force. The mechanism was elegant, mathematically consistent, and it solved a problem that had plagued particle physics for years. How do the W and Z bosons, the carriers of the weak nuclear force, have mass when the gauge symmetry of the theory seems to require them to be massless? The answer was spontaneous symmetry breaking. The Higgs field, sitting at its non-zero vacuum value, breaks the electroweak symmetry. The W and Z bosons interact with the field and acquire mass. The photon does not interact with the field in this way and remains massless. The symmetry is not absent from the theory, it is hidden, broken spontaneously by the vacuum state, not explicitly by the equations. The mechanism predicted the existence of a new particle, the Higgs boson, the quantum excitation of the Higgs field. But it did not predict the particle's mass. The Higgs mass is a free parameter of the Standard Model. It could, in principle, have been anywhere from a few gigaelectronvolts to a few hundred gigaelectronvolts. The theory gave no guidance. Only experiment could determine the value. The search lasted 48 years. From 1964 to 2012, nearly half a century of theoretical development, experimental design, and technological innovation, all directed at finding one particle and measuring one number. The Large Electron-Positron Collider at CERN searched for the Higgs in the 1990s and set a lower bound of approximately 114 gigaelectronvolts. The Tevatron at Fermilab searched in the 2000s and produced intriguing hints but no conclusive discovery. Then came the Large Hadron Collider, the most complex and most expensive scientific instrument ever built. A circular tunnel 27 kilometers in circumference, 100 meters underground, spanning the border between France and Switzerland. Inside the tunnel, 2 beams of protons travel in opposite directions at 99.999999% of the speed of light. They collide at 4 points around the ring, where enormous detectors, ATLAS and CMS, each weighing thousands of tons, record the debris of the collisions. The LHC was designed to find the Higgs boson. It was built for this purpose. Billions of dollars were spent. Thousands of physicists and engineers worked for decades. And on July 4, 2012, in a packed auditorium at CERN, the directors of the ATLAS and CMS experiments announced, independently, that they had found it. The mass was approximately 125 gigaelectronvolts. The measurement was confirmed by both detectors with a statistical significance of 5 sigma, meaning the probability that the signal was a random fluctuation was approximately 1 in 3.5 million. The particle was real. The mass was 125. The auditorium erupted. Peter Higgs, sitting in the audience at age 83, wept. The discovery was announced on news broadcasts around the world. The Nobel Prize in Physics was awarded the following year to Higgs and Englert. The Standard Model was complete. In the days and weeks that followed, as the initial euphoria subsided and the theorists began running the numbers, a quieter conversation started in the corridors and coffee rooms of physics departments. The conversation was about the number 125 and what it meant for the stability of the universe. 125 was right in the middle of the danger zone. If the Higgs had been heavier, say 130 or 140 gigaelectronvolts, The effective potential would curve upward at all field values, and the vacuum would be absolutely stable. If the Higgs had been lighter, say 115 or below, the vacuum would be clearly unstable, and vacuum decay would be a more immediate concern. 125 sits on the metastable line, the region where the effective potential develops a second minimum at extremely high field values, separated from the current vacuum by a barrier of enormous height but finite width. Joseph Likon, a theoretical physicist at Fermilab, was one of the first to discuss the implications publicly. At a meeting of the American Association for the Advancement of Science in 2013, he stated that the universe wants to be in a different state. He described the electroweak vacuum as potentially a fundamentally unstable place to be, and noted that the measured Higgs mass placed the universe right at the edge of stability. The statement made headlines. The headlines were predictably sensationalized. Scientists say universe could be destroyed at any moment. That is not what Likon said. What he said was that the mathematics of the Standard Model, combined with the measured Higgs mass, places the universe in a metastable state. The decay rate is extraordinarily slow. The universe is not about to be destroyed, but it is not in its ground state. It is in a state that is, on cosmological timescales, temporary. Temporary. In a universe that may exist forever. The tension in that sentence is the tension at the heart of this entire subject. The question that follows naturally from the metastability result is whether anything could accelerate the process. Whether there is some mechanism, some event, some catastrophe that could trigger vacuum decay before the exponentially long natural decay time. The answer is yes. In principle, vacuum decay can be catalyzed. The natural tunneling rate is the rate at which the field spontaneously tunnels through the barrier in a region of empty space at zero temperature. But if there is a source of extreme energy density, if there is a process that temporarily raises the Higgs field to a value closer to the top of the barrier, the tunneling probability increases. The barrier effectively becomes thinner. The decay rate goes up. What kinds of processes could do this? Any process that concentrates an enormous amount of energy in a very small volume. Black hole formation. The collapse of a massive star into a black hole produces energy densities in the vicinity of the singularity that approach the Planck scale, the energy scale at which quantum gravity effects become important, and which is far above the instability scale of the Higgs potential. Near the singularity, the local energy density is more than sufficient to push the Higgs field over the barrier. But does this actually trigger vacuum decay? The answer is complicated and the subject of active research. The singularity inside a black hole is hidden behind an event horizon. Whatever happens at the singularity stays inside the horizon. Even if vacuum decay is triggered at the singularity, the bubble of true vacuum that forms would be trapped inside the black hole, unable to escape past the event horizon. The bubble would expand, but it would expand into the interior of the black hole, not into the external universe. The rest of the universe would be safe. This argument is not airtight. It depends on the classical description of black holes being correct at the relevant scales. If quantum gravity modifies the behavior of spacetime near the singularity, if the event horizon is not a perfect boundary, if information or energy can leak out through mechanisms related to Hawking radiation or other quantum effects, then the safety argument weakens. The honest answer is that we do not fully understand what happens to the Higgs field in the immediate vicinity of a black hole singularity, because we do not have a complete theory of quantum gravity. Cosmic ray collisions. Ultra-high energy cosmic rays, protons accelerated to enormous energies by astrophysical processes, occasionally collide with other particles at energies far exceeding what the LHC can produce. The highest energy cosmic ray ever detected, the "Oh my God" particle, observed in 1991, had an energy of approximately 3 × 10⁻20 electron volts, roughly 40 million times the energy of the LHC. These collisions occur naturally in the upper atmosphere and throughout the universe. If high-energy collisions could trigger vacuum decay, the fact that the universe still exists after 13.8 billion years of cosmic ray bombardment provides strong evidence that they cannot. This argument, sometimes called the cosmic ray bound, is one of the most reassuring observations in this entire subject. Nature has been running particle physics experiments at energies far beyond our laboratory capabilities for billions of years. The universe has survived them all. Whatever the LHC does, cosmic rays have already done it more energetically and more frequently. If the LHC could trigger vacuum decay, the universe would have ended long ago. The cosmic ray bound does not apply to all possible triggers, however. It applies to point-like collisions at high energies. It does not apply to sustained, volume-filling energy densities of the kind that might be produced by, for example, the collision of 2 black holes, or the extreme conditions inside a neutron star merger, or the hypothetical energy densities that existed in the first fractions of a second after the Big Bang. The early universe is a particularly interesting case. During inflation, the Higgs field was subject to enormous quantum fluctuations, driven by the exponentially rapid expansion of space. Some regions of the inflating universe could have been pushed to field values above the instability scale. If the Higgs field in those regions rolled past the barrier and into the true vacuum, bubbles of true vacuum would have formed during inflation. Those bubbles would have expanded and could, in principle, have consumed the entire inflationary patch that became our observable universe. The fact that this did not happen, the fact that we exist in a universe with the Higgs field at the false vacuum value, constrains the dynamics of inflation and the Higgs field during the inflationary epoch. It tells us something about the energy scale of inflation, about the coupling between the Higgs field and the inflaton, and about the initial conditions of the universe. The survival of the false vacuum through inflation is not trivial. It is a constraint on cosmological models, and it is a constraint that is actively used in current research to test and refine inflationary theories. There is a related question that pushes the problem in a direction that is less about the far future and more about the present. It has to do with the fact that the universe is not empty. It contains structures: stars, galaxies, black holes, neutron stars, magnetic fields, gravitational waves. And some of these structures create conditions that, while far below the instability scale, are still relevant to the stability calculation. The relevant concept is the thermal correction to the effective potential. At non-zero temperature, the effective potential of the Higgs field is modified. The barrier between the false vacuum and the true vacuum changes shape. At very high temperatures, the barrier can disappear entirely, and the only minimum of the potential is at zero field value. This is the restored symmetry phase. At intermediate temperatures, the barrier exists but is lower. At zero temperature, the barrier is at its maximum height. The interior of a neutron star, where temperatures can reach billions of degrees and densities exceed nuclear density, is a natural laboratory for studying the thermal corrections to the Higgs potential. At these temperatures, the effective potential is modified, and the barrier between the false vacuum and any deeper minimum is altered. Some researchers have studied whether neutron star interiors could catalyze vacuum decay through thermal activation, a classical process in which the system climbs over the barrier using thermal energy rather than tunneling through it. The conclusion, so far, is that neutron star temperatures are far too low to produce any meaningful probability of thermal activation. The barrier height is on the order of 10 to the 40 gigaelectronvolts, and the temperatures inside neutron stars are on the order of 10 to the -3 gigaelectronvolts. The thermal energy is roughly 43 orders of magnitude too small to overcome the barrier. The neutron star would need to be approximately 10 to the 40 degrees hotter, a temperature that exceeds the Planck temperature and therefore exceeds the regime in which any known physics applies. Neutron stars are safe. The Sun is safe. The LHC is safe. Cosmic rays have confirmed this. Every known astrophysical process has been evaluated and found incapable of triggering vacuum decay. The universe, as far as current physics can determine, is safe from any externally triggered decay event. The only danger is the spontaneous one, the quantum tunneling. The slow, patient, exponentially unlikely event that will happen given enough time, but that will not happen on any timescale relevant to human civilization or even to the lifetime of the stars. But the word safe carries an asterisk. The asterisk says, unless there is new physics we do not know about. And there is very good reason to believe there is new physics we do not know about. The Standard Model is not a complete theory. It does not include gravity. It does not explain dark matter. It does not explain dark energy. It does not explain the matter-antimatter asymmetry of the universe. It does not explain neutrino masses, which have been confirmed experimentally, but require extensions to the Standard Model. It does not explain the hierarchy problem, the question of why the Higgs mass is so much lighter than the Planck mass when quantum corrections should drive it upward. It does not explain the strong CP problem, the question of why the strong nuclear force respects a symmetry it is not required to respect. Each of these open problems points to physics beyond the Standard Model. New particles, new forces, new fields. And any new physics that couples to the Higgs field modifies the effective potential. New particles that interact with the Higgs change the running of the self-coupling. They can stabilize the potential, making the universe absolutely stable. Or they can destabilize it further, making the barrier thinner and the decay rate faster. Supersymmetry, one of the most studied extensions of the Standard Model, generally stabilizes the Higgs potential. If supersymmetric particles exist at energies not too far above the current collider reach, they would modify the running of the Higgs self-coupling in a way that prevents it from turning negative. The universe would be stable. The metastability crisis would be averted. But supersymmetry has not been observed. The LHC has searched extensively for supersymmetric particles and found nothing. The simplest supersymmetric models have been ruled out. More complex ones remain possible, but are increasingly constrained. If supersymmetry exists, it is hiding. And if it does not exist, the Higgs potential is not stabilized by it, and the metastability result stands. Other new physics scenarios have different effects. Extra dimensions, composite Higgs models, new gauge interactions, each one changes the potential in a specific, calculable way. The landscape of possibilities is vast, and in many of those possibilities, the vacuum is less stable than the Standard Model alone predicts. The honest statement is this: we know the universe is metastable if the Standard Model is the whole story. We do not know whether the Standard Model is the whole story. The measurements that would resolve the question require either finding new particles at higher energies, which requires more powerful colliders than currently exist, or measuring the existing parameters, particularly the top quark mass, with precision sufficient to determine the fate of the universe to the necessary confidence level. Neither has been achieved. Both are being pursued. The fate of the universe is an experimental question. The experiment has not been completed. There is a dimension of the vacuum decay problem that is rarely discussed, but that connects it to one of the most profound questions in cosmology. The question of fine-tuning. The question of why the universe has the properties it has, and whether those properties are inevitable, accidental, or selected. The Higgs mass of 125 gigaelectronvolts places the universe in the metastable zone. But it does not merely place it in the metastable zone. It places it very close to the boundary between stability and metastability. The measured values sit within a few gigaelectronvolts of the critical line, the precise boundary in the parameter space of Higgs mass versus top quark mass that separates the stable region from the metastable region. This near criticality has attracted significant attention. Why should the universe sit so close to the boundary? If the Higgs mass and the top quark mass were determined by some random process, there is no particular reason they should land near the critical line. They could be anywhere in the allowed parameter space. The fact that they sit near the boundary suggests either a coincidence or a deeper principle. Some physicists have proposed that near criticality is a feature of the dynamics of the Standard Model at very high energies. If the Higgs self-coupling and its derivative, the beta function, both approach zero at the Planck scale, the energy scale at which quantum gravity effects become important, this would place the Higgs mass almost exactly at the critical value. This scenario is called asymptotic safety, or, in some formulations, Higgs criticality, and it has been studied extensively. The measured values of the Higgs and top quark masses are consistent with this scenario, though not uniquely predicted by it. If Higgs criticality is real, it would mean that the universe is not accidentally near the boundary. It is there because the fundamental physics drives it there. The Higgs mass is not a random number. It is a consequence of a deep principle relating the Standard Model to Planck scale physics. The metastability of the vacuum would not be an accident. It would be a prediction. This is an extraordinary possibility. It would connect the mass of the Higgs boson, measured in a laboratory at CERN, to the physics of quantum gravity, the most elusive and least understood frontier in all of physics. It would mean that the number 125.1, the number that tells us the vacuum is metastable, is not merely a measurement, it is a message from the Planck scale, from the energy regime where gravity and quantum mechanics merge, telling us something about the deepest structure of reality. Whether this interpretation is correct remains unknown. The measurements are not yet precise enough to confirm or refute Higgs criticality, but the possibility is there, and the possibility that the instability of the vacuum is not an accident but a feature, not a defect but a design principle, is one of the most tantalizing clues in all of modern physics. There is a way to think about vacuum decay that does not involve equations or quantum field theory or collider measurements. It involves ice. Consider a glass of water that has been cooled very carefully, very slowly, to a temperature below 0 degrees Celsius, but that is not frozen. This is called supercooled water. It exists in a metastable state. The stable state, the lowest energy state, is ice. But the water has not found its way there, because the transition from liquid to solid requires a nucleation event. A tiny crystal of ice must form first, a seed around which the rest of the water can crystallize. If there are no impurities, no vibrations, no disturbances of any kind, supercooled water can remain liquid at temperatures far below its freezing point. It looks like water. It behaves like water. It is, in every observable way, indistinguishable from normal liquid water. But it is not in its lowest energy state. It is waiting. Then you tap the glass, or drop in a single grain of dust, or breathe on it too hard, and the water freezes. Not slowly, from the outside in, the way water normally freezes. Explosively, nearly instantaneously. The nucleation event triggers a phase transition that propagates through the entire volume of water at a speed that looks, on video, like magic. One moment liquid, the next moment solid. The transition is so fast that cameras recording at thousands of frames per second can barely capture it. The universe is the supercooled water. The false vacuum is the liquid state. The true vacuum is the ice. The bubble nucleation event is the grain of dust, the tap on the glass, the tiny disturbance that triggers the phase transition. And the expanding bubble of true vacuum is the crystallization front, propagating outward, converting the metastable state into the stable state, irreversibly, completely, at the speed of light. The analogy is not perfect. No analogy ever is. The physics of vacuum decay is quantum mechanical. The physics of freezing water is classical. The speed of propagation is different. The dimensionality is different. The consequences are different. But the structural similarity is precise. Both systems are in a metastable state. Both have a lower energy state available. Both require a nucleation event to trigger the transition. And both, once triggered, undergo a phase transition that transforms the entire system irreversibly. The universe is supercooled. It has been supercooled since the moment the Higgs field settled into its current vacuum value, approximately 10 to the minus 11 seconds after the Big Bang. It has been in this state for 13.8 billion years. It may remain in this state for 10 to the 100 years or longer. But it is not in its ground state. It is not at the bottom. It is balanced, patiently, precariously, on a shelf above the true bottom, held there by a barrier that quantum mechanics says is not impenetrable. The water is waiting to freeze. The tap has not yet come. But the glass is not empty of time. And time, in a universe with quantum mechanics, is the one thing that is never on your side. The water is waiting to freeze. The tap has not yet come. But the glass is not empty of time. And time, in a universe with quantum mechanics, is the one thing that is never on your side. The analogy with ice is more than illustrative. It points to something that actually happened, because the universe has already undergone phase transitions. Not one, several. And each one rewrote the laws of physics as completely as vacuum decay would rewrite them today. In the first fraction of a second after the Big Bang, the universe was extraordinarily hot. So hot that the fundamental forces of nature, the forces that today appear as four distinct interactions, were unified. At the highest energies, there was no distinction between the electromagnetic force and the weak nuclear force. They were one force, the electroweak force, mediated by four massless gauge bosons moving freely through a Higgs field that sat at zero. The symmetry was unbroken. The universe was in a different vacuum state. Then the universe cooled. At approximately 10 to the minus 12 seconds after the Big Bang, the temperature dropped below approximately 159 gigaelectronvolts, and the electroweak phase transition occurred. The Higgs field rolled from its zero value to its non-zero vacuum value of 246 gigaelectronvolts. The symmetry broke. The W and Z bosons acquired mass. The photon remained massless. The electromagnetic force and the weak force separated into the two distinct forces we observe today. The entire character of particle interactions changed. The universe before the transition and the universe after the transition obeyed different rules. This actually happened. This is not speculation. The electroweak phase transition is a confirmed prediction of the Standard Model, supported by precision measurements at particle colliders. The details of the transition, whether it was a smooth crossover or a violent first-order phase transition with bubbles and collisions, depend on parameters that are still being refined. But the transition itself is established physics. The universe underwent a fundamental change of state 13.8 billion years ago that reorganized the forces of nature and gave matter its current properties. And there was an earlier transition. At approximately 10 to the minus 6 seconds after the Big Bang, the temperature dropped below approximately 150 megaelectronvolts, and the QCD phase transition occurred. Quarks and gluons, which had been moving freely in a quark-gluon plasma, became confined inside protons and neutrons. The character of matter changed from a soup of free quarks to the hadronic matter we observe today. This transition is also established physics, confirmed by lattice QCD calculations and by the creation of quark-gluon plasma in heavy ion collisions at RHIC and the LHC. Still earlier, if grand unified theories are correct, there may have been a GUT phase transition at approximately 10 to the minus 36 seconds, when the strong force separated from the electroweak force. And before that, if string theory or some other theory of quantum gravity is correct, there may have been a transition at the Planck time, 10 to the minus 43 seconds, when space-time itself crystallized from whatever preceded it. Each transition changed the rules. Each transition was a vacuum decay of sorts, a transition from a higher energy vacuum state to a lower energy one. Each transition was irreversible. The universe before the transition was destroyed. Not in the sense that matter was annihilated, but in the sense that the physical laws governing that matter were replaced. The quark-gluon plasma before the QCD transition was not destroyed by the transition. It was transformed into something that obeys different rules. The particles before the electroweak transition were not destroyed. They were given mass where they had none. Vacuum decay, as we have been discussing it, would be the next transition in this sequence, the next step down, the next crystallization of the vacuum into a deeper, more stable state. It would change the rules again. It would transform matter again. It would be, from the perspective of any observer, indistinguishable from annihilation, because the observer depends on the current rules, and the current rules would no longer apply. The universe has done this before, multiple times. Each time, it destroyed the version of physics that preceded it and replaced it with something different. Each time, the transition was total, irreversible, and from the perspective of any hypothetical observer on the other side, catastrophic. We are the beneficiaries of the most recent transition. The electroweak phase transition gave us the masses we need. The QCD transition gave us protons and neutrons. The chain of vacuum transitions that preceded our existence is the chain that made our existence possible. We live in the aftermath of cosmic phase transitions. We are made of their products. We are, in a very literal sense, the children of vacuum decay. And the universe may have one more transition left. There is something worth saying about the emotional register of this subject that most physics papers do not address, but that anyone who has spent time with the material has felt. The knowledge that the universe is metastable produces a specific kind of unease. Not the immediate, pulse-quickening fear of a predator or a cliff edge, something deeper and quieter. The unease of living in a house that you have been told has a structural defect. Not a defect that will cause collapse today or tomorrow or this century. A defect on a timescale so long that it is meaningless in practical terms. But a defect that is there, in the foundations, confirmed by engineers, measured and calculated, and published in a report that you keep in a drawer and try not to think about. The unease is not rational in the actuarial sense. The probability of vacuum decay affecting anything you care about is so small that it is not meaningfully different from zero. You will die of old age. The sun will burn for another 5 billion years. The stars will shine for trillions of years. Vacuum decay is a problem for timescales so long that the word problem loses its meaning. By any reasonable measure, the metastability of the vacuum is not your problem. But the knowledge changes something. It changes the way you think about permanence. It changes the way you think about the foundation of reality. The laws of physics, the rules that govern everything, the constants and forces and symmetries that make atoms and stars and thoughts possible. Those rules feel permanent. They feel foundational. They feel like the one thing that does not change in a universe where everything changes. And the metastability result says they are not permanent. They are conditional. They are the product of a vacuum state that is not the lowest vacuum state. They are the product of a field value that is not the most energetically favourable value. They persist because there is a barrier, and the barrier is very tall, and the tunnelling probability is very small. But persistence is not permanence, and the laws of physics, the rules you build your entire understanding of reality on, are as contingent and as potentially temporary as the vacuum state that produces them. This realization sits differently than other existential risks. An asteroid impact is terrifying, but it does not change the laws of physics. The sun's eventual death is melancholic, but it does not rewrite the rules of chemistry. The heat death of the universe is bleak, but it leaves the rules intact even as it removes everything that the rules once governed. Vacuum decay is different. It changes the rules themselves. It attacks the foundation, not the structure. It says the universe is not merely mortal. The universe's physics is mortal. The laws that make you possible can unmake you and everything like you by simply shifting to a different, deeper, more stable configuration. There is no precedent for this kind of risk in human experience. We have words for the destruction of things. We have words for the end of life. We do not have words for the end of the conditions that make things and life possible. Vacuum decay is not an extinction event. It is not a catastrophe. It is a phase transition. And the language of catastrophe, the language of destruction and loss and death, does not quite apply, because destruction implies that something is broken. Vacuum decay does not break anything. It replaces everything. It substitutes one set of rules for another. It is not violent. It is editorial. The universe revises its own text, and the previous edition is not destroyed, but overwritten. The distinction matters because it changes the nature of the loss. In a catastrophe, you lose the things that existed under the old rules. In a phase transition, you lose the rules themselves. The first is a tragedy. The second is something for which we do not have a word. Let us return to the physics and ask a question that pushes toward the boundary of what is currently known. What happens to black holes during vacuum decay? Black holes are the most extreme objects in the universe. They are regions where the curvature of space-time is so intense that nothing, not even light, can escape. The event horizon, the boundary of the black hole, is a one-way membrane. Things fall in, nothing comes out. The interior, according to general relativity, contains a singularity, a point of infinite density where the known laws of physics break down. When a vacuum decay bubble encounters a black hole, the interaction is extraordinary and not fully understood. The bubble wall, expanding at the speed of light, cannot enter the black hole's event horizon from the outside in the usual sense. The event horizon is a causal boundary. Nothing from outside can influence the interior. The bubble wall, despite its enormous energy, respects causality. It cannot penetrate the horizon from the outside. But the situation is more subtle than this simple picture suggests. The vacuum decay changes the space-time outside the black hole. The energy density of the new vacuum is different from the old vacuum. The cosmological constant, if it changes in the transition, alters the large-scale geometry of space-time. The black hole finds itself embedded in a new space-time with different asymptotic properties. Some calculations suggest that the bubble wall wraps around the black hole, enveloping it completely. The black hole continues to exist inside the bubble, but the space-time outside it is now the true vacuum. The black hole's properties, its mass, charge, and angular momentum, are defined by the space-time it inhabits. In the new vacuum, these properties may be differently related to the geometry. The black hole might evaporate differently. It might radiate differently. Its Hawking radiation spectrum would change because the particle masses that appear in the radiation are determined by the vacuum state, which has changed. Other calculations, particularly those by Ruth Gregory, Ian Moss, and Benjamin Withers, have shown something more dramatic. Black holes can act as seeds for vacuum decay. The curved spacetime near a black hole, particularly near its event horizon, can lower the barrier for bubble nucleation. The tunneling probability near a black hole is higher than in empty space. The black hole catalyzes the decay. This result, published in 2014 and refined in subsequent papers, means that black holes are not passive bystanders in the metastability story. They are active participants. They are the places in the universe where vacuum decay is most likely to begin. Not because the energy is high enough to push the field over the barrier classically, but because the curvature of spacetime near the horizon modifies the tunneling calculation in a way that enhances the rate. The enhancement is significant, but not alarming. For stellar mass black holes, the catalysis increases the tunneling rate by a factor that is large in relative terms, but still leaves the absolute rate exponentially small. The half-life is still vastly longer than the age of the universe. But the result is theoretically important, because it identifies a specific physical mechanism by which the geometry of spacetime and the stability of the vacuum interact. General relativity and quantum field theory, the two pillars of modern physics, each contribute to the calculation. The answer depends on both. For microscopic black holes with masses near the Planck mass, the catalysis effect could be much larger. Microscopic black holes have extreme curvature near their horizons and correspondingly large effects on the tunneling rate. If microscopic black holes were produced in the early universe, as some cosmological models predict, they could have served as nucleation sites for vacuum decay bubbles during the first moments of cosmic history. The fact that the vacuum did not decay at that time constrains the abundance and properties of primordial microscopic black holes. And there is an even more speculative possibility. If the black hole evaporates completely through Hawking radiation, what happens at the endpoint? A black hole that starts with stellar mass will evaporate over approximately 10 to the 67 years. As it shrinks, the curvature at the horizon increases. The catalysis effect grows stronger. In the final moments of evaporation, as the black hole approaches Planck mass, the effect could become dominant. The death of a black hole might trigger the birth of a vacuum decay bubble. This is not established physics, it is speculation at the boundary of current theory. The final moments of black hole evaporation are governed by quantum gravity, which we do not have a complete theory of. The Gregory-Moss-Withers catalysis calculation is performed in the semi-classical regime, where quantum field theory is applied on a classical space-time background. As the black hole approaches Planck mass, the semi-classical approximation breaks down. We do not know which universe down. We do not know what happens. But the possibility is there, written into the equations, waiting for a complete theory to either confirm or deny it. And if it is correct, then every black hole in the universe is a potential detonator. A seed that, at the moment of its death, might trigger the phase transition that rewrites physics. The universe contains approximately 40 billion black holes. Each one is slowly evaporating. Each one will eventually die. And each death, if the speculation is correct, carries a non-zero probability of ending everything. That probability is almost certainly negligible. The numbers, when they are eventually calculated by a complete theory of quantum gravity, will almost certainly show that black hole death does not trigger vacuum decay with any meaningful probability. But the structure of the problem, the way it connects black hole physics to vacuum stability to quantum gravity, is a sign of how deeply the metastability question penetrates into the foundations of physics. It is not an isolated result about one number measured at CERN. It is a thread that, when pulled, unravels into the deepest open questions in theoretical physics. There is a perspective on vacuum decay that comes not from physics, but from the philosophy of science, and it illuminates something about the nature of scientific knowledge that the technical papers tend to obscure. The metastability of the vacuum is a prediction. It is derived from the standard model using established mathematical techniques applied to measured parameter values. The derivation is peer-reviewed, published, and reproduced by multiple independent groups. By every standard criterion of scientific knowledge, the metastability of the vacuum is a well-established result. And yet it is a prediction about a process that has never been observed, that cannot be experimentally tested, and that occurs on a timescale longer than the age of the universe by a factor of at least 10 to the 90. The prediction is derived from physics that has been tested at energies up to approximately 13,000 gigaelectronvolts, the energy frontier of the LHC. The instability of the vacuum occurs at energies of approximately 10 to the 10th gigaelectronvolts, approximately 7 orders of magnitude above the LHC energy. The extrapolation from the tested regime to the relevant regime spans a vast range. The prediction relies on the assumption that no new physics intervenes in that range. Is this a reliable prediction? The mathematical framework is robust, the calculations are correct, the extrapolation follows from the equations. But extrapolations over 7 orders of magnitude in energy into a regime that has never been probed experimentally carry an inherent risk. The history of physics is full of examples where well-motivated extrapolations from known physics into new regimes turned out to be wrong. Classical physics extrapolated smoothly from macroscopic scales failed at atomic scales. Newtonian gravity extrapolated smoothly from terrestrial scales failed at relativistic scales. Each time, the existing framework was correct within its tested domain and incorrect beyond it. The metastability prediction might be correct. It is derived carefully from well-tested physics using established techniques. But it might also be an artifact of extrapolating the standard model beyond its domain of validity. New physics at intermediate energies, physics that we have not yet discovered, could stabilize the vacuum completely, or could accelerate the decay dramatically. Without experimental data at the relevant energies, we cannot distinguish between these possibilities. This is not a criticism of the physicists who performed the calculation. They are explicit about the assumptions. They state clearly that the result depends on the standard model being the complete description of physics up to the instability scale. They acknowledge that new physics could change the answer. The papers are honest. The science is sound. But the popular reception of the result often strips away the caveats. The universe could end at any moment. The vacuum is unstable. We are living in a metastable death trap. These headlines are not wrong exactly, but they present a conditional prediction as an unconditional fact. They present an extrapolation as a measurement. They present a possibility as a certainty. The truth is more nuanced and, in its nuance, more interesting. The standard model, applied naively to high energies, predicts metastability. This is a remarkable and important result. It tells us that the standard model, by itself, contains the seeds of its own incompleteness. A complete theory, a theory that describes physics at all energies, would either stabilize the vacuum or explain why the metastability is a feature rather than a bug. The metastability prediction is not just a prediction about the fate of the universe. It is a signpost pointing toward new physics. It is the standard model telling us it is not the final word. And that, perhaps, is the most constructive way to think about vacuum decay. Not as a threat, not as an existential risk, not as a cosmic horror story, but as a clue. A clue that the physics we know is not the physics that is. A clue that somewhere between the energies we can probe and the energies where the vacuum turns unstable, there are discoveries waiting. Particles we have not found, forces we have not measured, symmetries we have not imagined. The metastability of the vacuum is the standard model's confession of incompleteness. And incompleteness, in science, is not a failure. It is an invitation. Let us talk about what the true vacuum looks like. Because this is where the conversation moves from abstract danger to concrete strangeness. If the Higgs field transitions to its true vacuum value, the new value is not 246 gigaelectronvolts. It is much larger. In the standard model calculation, the true vacuum sits at a field value of approximately 10 to the 10th gigaelectronvolts, or higher, depending on the exact location of the second minimum. The precise value is model-dependent and uncertain, but it is enormously larger than the current vacuum value. When the Higgs field shifts to this new value, the masses of all fundamental particles change. The electron, currently massing approximately 0.511 megaelectronvolts, would acquire a new mass determined by its coupling to the new vacuum value. The new mass would be approximately 10 to the 8th times larger than the current mass. The electron would be as heavy as a current-day uranium atom. An atom with electrons that heavy cannot exist in any form recognizable as chemistry. The Bohr radius, the characteristic size of an atom, is inversely proportional to the electron mass. Multiply the electron mass by 10 to the 8th, and the atom shrinks by a factor of 10 to the 8th. Atoms in the true vacuum would be roughly 10 to the minus 18th meters in size, 100 million times smaller than current atoms, smaller than a proton. The concept of an atom as we know it would cease to be meaningful. The weak nuclear force would also change. The W and Z bosons, which mediate the weak force, would acquire masses proportional to the new vacuum value. They would become extraordinarily heavy, making the weak force extraordinarily short-ranged, far shorter range than it already is. Beta decay, the process by which neutrons decay into protons, would be suppressed. Nuclear physics would be different. The periodic table would not exist. The strong nuclear force, interestingly, would be less directly affected. The strong force is mediated by gluons, which are massless and remain massless in the true vacuum because they do not couple directly to the Higgs field. But the quarks that feel the strong force would have different masses, and those different masses would change the dynamics of quark confinement, the formation of protons and neutrons, and the properties of nuclear matter. The bottom line is that the true vacuum universe is not a slightly different version of our universe. It is a radically different universe. The particles are different. The forces are different. The structures that conform are different. There are no atoms as we know them. There are no stars as we know them. There is no chemistry. There is no biology. There is nothing recognizable. Whether the true vacuum permits any kind of structure at all is an open question. Some analyses suggest that the true vacuum universe might be completely featureless, a uniform soup of ultra-heavy particles with no mechanism for forming bound states or larger structures. Others suggest that new kinds of bound states might form, governed by the strong force, with properties entirely different from anything in our experience. Without a complete understanding of the true vacuum physics, we cannot say what the interior of a vacuum decay bubble looks like in the long run. What we can say is that it does not look like us. It does not contain us. It does not permit us. Whatever exists inside the bubble, it is not a universe hospitable to the kind of matter, the kind of chemistry, the kind of life that depends on the Higgs field having a vacuum value of 246 gigaelectronvolts. That specific number, that specific value, is the foundation on which everything we know is built. Change it, and the building does not just crumble. The building materials themselves cease to exist. There is a connection here to the anthropic principle that deserves explicit attention. The anthropic principle, in its weak form, states that the observed properties of the universe must be compatible with the existence of observers. We observe a universe with a Higgs vacuum value of 246 gigaelectronvolts because only a universe with that value, or something close to it, produces atoms, molecules, stars, planets, and observers. If the universe can exist in multiple vacuum states, and if different regions of the universe might sit in different states, then the anthropic principle provides an explanation for why we find ourselves in the false vacuum rather than the true vacuum. The true vacuum does not contain observers, only the false vacuum does. So of course we find ourselves in the false vacuum. We could not find ourselves anywhere else. This reasoning is seductive but slippery. It explains why we observe the false vacuum, but it does not explain why the false vacuum exists in the first place, why the Higgs potential has the shape it has, or why the parameters of the standard model take the values they take. It also does not eliminate the metastability. The anthropic principle explains our current location in the landscape. It does not protect us from sliding to a different location. We are here because this is where observers can be. But being here does not mean staying here. The landscape does not owe us permanence. It gave us a ledge. It did not promise the ledge would last. There is one more aspect of this subject that requires discussion, because it represents the frontier of current research, and because it connects vacuum decay to the most ambitious project in contemporary physics. The connection between the Higgs field metastability and quantum gravity. The instability scale of the Higgs potential, the energy at which the self-coupling turns negative, is approximately 10 to the 10 to the 10 to the 12 gigaelectronvolts. The Planck scale, the energy at which quantum gravity effects become important, is approximately 10 to the 19 gigaelectronvolts. These two scales are not identical, but they are not wildly different by particle physics standards, where energy scales can span 50 or 60 orders of magnitude. The proximity of the instability scale to the Planck scale means that the behavior of the Higgs potential in the critical region, the region where the potential turns over and develops the second minimum, may be affected by quantum gravity. The standard model calculation of the running couplings assumes that gravity can be ignored. At the energies relevant for the instability, gravity is extremely weak, and this assumption is justified. But as you approach the Planck scale, gravity becomes strong, and the standard model calculation is no longer reliable. If quantum gravity modifies the effective potential of the Higgs field near the Planck scale, the stability analysis could change. The potential might turn back up at very high field values, stabilized by Planck scale physics, or it might turn down more steeply, destabilized by gravitational effects. Without a complete theory of quantum gravity, we cannot calculate which. This means that the fate of the universe, the question of whether the vacuum is truly metastable or ultimately stable, may depend on quantum gravity. The answer may not be accessible to particle physics alone. It may require understanding the unification of gravity and quantum mechanics, the problem that has resisted solution for nearly a century. String theory, the leading candidate for a theory of quantum gravity, provides a framework in which the effective potential of scalar fields can be calculated, including gravitational effects. In the string theory landscape, the Higgs field is one of many scalar fields, and the vacuum state of the universe is determined by the values of all of them. The landscape of possible vacua in string theory is enormous, estimated to contain 10 to the 500 or more distinct vacua, each with different physical laws and different vacuum stability properties. In this framework, the metastability of the Higgs vacuum is one feature of one vacuum among an essentially infinite number. The question of whether our vacuum decays becomes a question about the topology of the string theory landscape near our vacuum. Are there neighbouring vacua? How high are the barriers? What are the tunnelling rates? These are calculable questions in principle, but the calculations require knowledge of the landscape that we do not possess. The vacuum decay problem, which started as a question about one number measured at CERN, has grown into a question about the fundamental nature of space-time, the origin of physical laws, and the ultimate fate of everything that exists. It connects a laboratory measurement to the deepest questions in physics. It asks whether the universe we live in is stable, and the answer depends on physics we have not yet discovered. That is the current state of knowledge. The universe is metastable according to the standard model. The standard model may not be the final theory. New physics could stabilize the vacuum or destabilize it further. The measurements needed to resolve the question are being pursued. The theoretical frameworks needed to complete the analysis are being developed. And, in the meantime, the Higgs field sits at its current value, 246 gigaelectronvolts, holding together every atom in your body, every star in the sky, every structure in the observable universe, balanced on a barrier that mathematics says is finite and that quantum mechanics says is penetrable. The universe is not in its lowest energy state. It is in a state that permits existence. Those two facts coexist. They coexist uncomfortably. And the discomfort is not a failure of understanding. It is an accurate reflection of what the physics says. The universe is slowly erasing itself. Not quickly, not urgently, not on any timescale that threatens anything you care about, but slowly, patiently, inevitably. In the mathematical sense, that inevitable applies to any event with non-zero probability and infinite available time. The measurement that revealed this was 125.1 gigaelectronvolts, a number written on a whiteboard, a number that completed the standard model, a number that won the Nobel Prize, a number that tells us, quietly, in the language of quantum field theory, that the ground beneath our feet is not the ground. It is a shelf. And the shelf, for all its solidity, for all the billions of years it has held, for all the stars and galaxies and lives it has supported, is not the bottom. The bottom is somewhere else, deeper, different, uninhabitable. And the distance between the shelf and the bottom is measured not in meters or miles or light years, but in gigaelectronvolts, in the value of a quantum field, in the mass of a particle discovered on July 4th, 2012, in a laboratory in Switzerland by thousands of physicists who had spent decades looking for it. They found it. They celebrated. They measured its mass. And the mass told them something about the universe that the universe had been keeping to itself for 13.8 billion years. The vacuum is not eternal. The laws of physics that govern your existence are not permanent. The stability of everything you see is not guaranteed by anything deeper than a barrier in a quantum field. A barrier that is high but not infinite, wide but not impassable, and patient, infinitely patient, in a universe that has nothing but time. You are made of a metastable vacuum. Your atoms are held together by a field that is not in its ground state. The forces that give you form are consequences of a symmetry breaking that may not be the final word. The universe that contains you is, in the most precise and technical and confirmed sense that modern physics can produce, temporary. Not temporary the way a human life is temporary. Not temporary the way a star is temporary. Temporary the way a supercooled liquid is temporary. Waiting, holding, persisting far beyond any reasonable expectation, but not permanent. Never permanent. And the number that tells you this, the number that separates you from the void, the number that holds the entire architecture of reality in place, is 125.1. Written on a whiteboard, measured in a collider, published in a paper, celebrated with champagne. Nobody mentioned what it meant. Now you know. There is a final layer to this story, and it is the layer that haunts theoretical physicists more than any calculation about tunneling rates or instability scales. It has to do with the multiverse, and specifically with what vacuum decay means in a universe that may not be the only one. If eternal inflation is correct, if the universe is one pocket in an infinite landscape of pocket universes, then vacuum decay is not just a local event. It is a cosmic process that has happened an infinite number of times across the multiverse. In some pockets, the Higgs field sits in a deep, stable minimum. Those pockets are eternal, in the sense that their vacuum never decays. In other pockets, the Higgs field sits in a shallow, metastable minimum. Those pockets are temporary. They last for a cosmically long time, long enough for stars and planets and life to form, but they are not permanent. They will eventually transition to a deeper vacuum. In still other pockets, the vacuum has already decayed. Those pockets contain the true vacuum, with its alien physics, its unrecognizable particles, its inhospitable laws. Nothing we would recognize as structure exists there. Nothing we would recognize as life. Just the deep vacuum, the true ground state, sitting quietly at the bottom of the energy landscape, empty and stable and permanent. If this picture is correct, then vacuum decay is not a catastrophe. It is the natural life cycle of a pocket universe. Pocket universes are born in inflation. They live for a finite time, however long, in a metastable state. They die when the vacuum decays. And the multiverse, the infinite collection of all pockets, continues. New pockets are born. Some are stable, some are metastable, some decay immediately. The process repeats forever. Vacuum decay is not the end of everything. It is the end of one island in an infinite archipelago. This perspective is either comforting or annihilating, depending on how you think about identity. If you identify with the universe, with this particular pocket, with the specific set of physical laws that allows your existence, then vacuum decay is annihilation. Everything you care about is in this pocket. When this pocket decays, everything you care about is gone. The fact that other pockets survive is irrelevant because you have no access to them, no communication with them, no relationship to them. They might as well not exist. But if you identify with the process, with the ongoing generation of pockets, with the infinite creativity of eternal inflation, producing universe after universe after universe, each with its own laws, each with its own possibilities, then vacuum decay is just a chapter ending. The book continues. Other chapters are being written. Other universes are hosting other observers, other thoughts, other forms of complexity that we cannot imagine. The loss of one pocket is the loss of one perspective, not the loss of perspective itself. Physicists, being human, tend to identify with the universe they live in. They care about the fate of this vacuum, these laws, these atoms, these stars. The multiverse perspective does not diminish that care. It contextualizes it. It says that the impermanence of our vacuum is not an anomaly. It is the default. Most vacua in the landscape are metastable. Most pocket universes will eventually decay. Permanence is the exception, not the rule. We live in a typical pocket, a pocket with a finite lifespan, a pocket that is, by the standards of the multiverse, ordinary. There is something liberating in that ordinariness, and something devastating. The liberation comes from knowing that the impermanence is not personal. The universe did not single us out for destruction. It did not design a flaw that threatens specifically us. The metastability is a generic feature of the landscape. We are not cursed, we are typical. The devastation comes from knowing that typical means temporary. And temporary, when applied to the foundation of your existence, to the laws that make your atoms hold together and your thoughts cohere, is a word that carries a weight that no amount of cosmological perspective can fully lighten. The universe is erasing itself, slowly, patiently, on a timescale so long that patience itself loses meaning. The erasure is not violent, it is not dramatic. It is quantum mechanical, a field sitting in a state that is not the lowest state, waiting for a fluctuation that will begin the transition. The fluctuation will come. In an infinite future, it must come. And when it comes, it will propagate at the speed of light, converting false vacuum to true vacuum, contingent physics to fundamental physics, temporary laws to permanent ones. Everything built on the temporary laws, every atom, every molecule, every star, every galaxy, every planet, every ocean, every cell, every thought, every feeling, every memory, every person who has ever lived or will ever live will be overwritten. Not destroyed, overwritten. The distinction is small from the perspective of the things being overwritten, but it is enormous from the perspective of the physics. Destruction leaves rubble. Overwriting leaves a clean page. A page on which different words are written. Words we cannot read. Words that describe a universe we cannot imagine. Words that mean nothing to us, and everything to whatever, if anything, exists in the true vacuum. The universe wrote us in pencil, beautifully, precisely, with extraordinary care and extraordinary complexity. Stars that burned for billions of years to produce the atoms in your body. Galaxies that assembled over cosmic time to create the environment in which your planet could form. Chemical processes that selected over billions of years of evolution for the specific molecular arrangements that produce thought and feeling and awareness. All of it written in pencil, on a page that the universe reserves the right to erase. The eraser is quantum mechanics. The pencil was the Big Bang. And the page, the vacuum, the field, the foundation, was never guaranteed to hold the writing. It was always metastable. It was always conditional. It was always, in the deepest physical sense, temporary. 125.1 gigaelectronvolts. The mass of the Higgs boson. The number that tells you the pencil was always pencil, that the writing was always erasable, that the page was always on loan. The loan is long, longer than anything you can imagine, longer than the age of everything that has ever existed, longer than the time between now and the death of the last star, longer than the time between the last star's death and the evaporation of the last black hole. But a loan, no matter how long, is not a gift. A loan is returned. A gift is kept. And the universe, according to the number written on a whiteboard at CERN, gave us a loan. We are living on borrowed vacuum, borrowed fields, borrowed laws, borrowed existence. The debt will be called in. Not today, not this eon, not this cosmic epoch, but eventually, in the fullness of infinite time. When quantum mechanics, patient beyond all patience, finds the fluctuation it has been waiting for. And the universe will erase itself, cleanly, completely, at the speed of light, without a sound, without a warning, without anyone left to remember that anything was ever written on the page at all. That is what 125.1 means. That is what the Higgs boson told us. That is what the standard model predicts, and what the measurements confirm, and what the mathematics demands. The universe is slowly erasing itself. And now you know the number that proves it.